Hi, my name is Mitchell Lord, and this is my lab report for Lab 2. Uh, the purpose of this lab was to analyze the motion of a projectile using Newton's second law. To conduct this experiment, I recorded myself throwing a basketball on a parabolic trajectory, then I analyzed it in Tracker, and then made computational models in GlowScript using Newton's second law. Here's a brief preview of my results. The orange trajectory is the computational model that didn't account for drag. The blue line is the experimental trajectory, and the gray line is the computational model that did account for drag. The physics principles we use in this lab center around Newton's second law, and we use those to update the ball's position and velocity during the loop in the code. We also use gravity since the ball is on Earth. The force of gravity acts downward on the ball throughout its motion. And we also use the force of drag to calculate the air resistance on the ball, which always acts in the opposite direction of the ball's velocity. Here are the equations we use. Newton's second law, F equals ma, and the position and velocity update formula come from Newton's second law. We also use formulas for drag and gravity. For the setup, the basketball is the system and everything else are the surroundings. I chose to use a table as my point of reference, or y equals 0. The coordinate system is centered at the center of the ball on the first frame after it leaves my hand, and I use a 10-inch tape measure to calibrate Tracker. Here are the initial conditions. The ball is initially at the origin. Here's the initial velocity, time equals 0. And here's the video. I put that in the Tracker, calibrated it, and set everything up. And then I went through frame by frame and tracked the center and then put the data I got from Tracker into GlowScript. For the coding part, I initialized all of the variables and started a time loop. And in each iteration of the time loop, I computed the net force acting on the ball as the force of gravity plus the force of drag. Then I used that force and Newton's second law to update the position and velocity of the ball. For the first computational model, the orange arc in the graph, I set b equals to 0 in the drag equation to model the trajectory of the ball as if gravity were the only force acting on it. For the second model, I tried a bunch of different values for b and ended up using b equals 0.1 because it best matched my experimental trajectory. Next, I gathered the data from those models and plotted it. Oh, and here's my main loop in the code where I use Newton's second law. Here's a video of the output. And again, here are the results. As you can see, the orange, the model that doesn't account for drag, overshoots the trajectory by a good bit and the range. But the model that does account for drag matches the experimental model quite closely. So yeah, like I said, the gravity only model overestimates the trajectory, and this does make sense because the drag force acts in the opposite direction of the velocity, which slows it down. And for takeaways, Newton's second law does well at predicting motion when all forces acting on the system are included in the calculations, and air resistance on a basketball is not negligible and affects the trajectory. For possible sources of error, there could have been tracker marking errors, like when I had to go through frame by frame and mark the center of the ball, I could have been slightly off at different frames, and that could have caused slight error. If there could have been a calibration error in Tracker, if I didn't perfectly calibrate it, could cause errors down the road, and camera errors, like if the phone was slightly tilted or not perfectly perpendicular to the plane of motion. What does it mean? Do any of my models predict a terminal velocity? And no, neither of my models predict a terminal velocity because my basketball was only in the air for about half a second. It didn't have enough time to reach terminal velocity. Um, a similar experiment that would predict terminal velocity would be dropping a lighter object or an object with more air resistance from a greater height. Um, and what does it mean? If the object were thrown straight up with the same initial speed, would the time the object takes to reach the table be the same, longer, or shorter? So here I calculate the initial speed in my experiment, which is 4.12 meters per second. The initial velocity in the y direction in my experiment was this, but in the straight up experiment, it would have been this. So since the ball starts and ends at the same height, we can use this to calculate the time. And in my experiment, it's 0.6 seconds, and the hypothetical 0.8. So the ball would take longer if it was thrown, take longer to reach the table if it were thrown straight up in the air. And here's the conclusion. So yeah, thank you.